Good morning, everybody. Thank you for being here today. This is part of our webinar series, and we're going to go over an introduction to wastewater math today. And so this is part of our series that is put on with funding through the Environmental Protection Agency. All right, so just a little bit about who we are. I'm with the Southwest Environmental Finance Center, and we're at the University of New Mexico within the School of Engineering. And we're based in Albuquerque, but I'm actually based in Billings, Montana. And as part of this project, we also have partners at Wichita State University Environmental Finance Center, and they also house the Heartland Environmental Justice Center, and they are in Wichita, Kansas. So thank you for being here. There's some of them here on this webinar as well. And myself, I am Tucker Colvin, and I'm a research scientist here at the Southwest Environmental Finance Center. And I'm based in Billings, Montana, leading work up here in EPA Region 8. And I've been with the Southwest Environmental Finance Center for quite a few years now, but I've also been a drinking water plant operator, and I'm still certified. And then also on today, we have AJ Barney, who is the research engineer at the Southwest Environmental Finance Center and is based in Albuquerque, and he is a certified wastewater operator. So he is also here today and is going to go over some of the content. And just really quickly about our program. This webinar is part of our new tribal wastewater program, and this is through funding from the EPA. And the goal of this is to provide training and technical assistance to tribal wastewater systems in EPA regions 6, 7, and 8. And this program includes trainings and technical assistance to tribes and utilities, really for the goal of prevent pollution, really with the goal of public health and environmental health. It's to also help tribes and utilities comply with environmental regulations and to build that internal technical, managerial, and financial capacity. A big chunk of this is also to help tribes and utilities access public funding to meet their infrastructure needs. And really, the goal is to just help you all, both for your compliance, environmental regulations, protecting the environment, and public health. So we're here to help you and help you with really whatever you need. So please reach out and let us know what we can assist you with. Oh, and down there is a link to our webpage for this project. So you can click that link or go to that website on that link or use that QR code. So, and you'll get to that page and you can learn more information about this specific program. All right, and some of the things we're doing for this is we're doing needs assessments, so meeting with you all to try to just go through your operations and your infrastructure to help you see what your biggest needs are. We're providing technical assistance for funding. It's a big part of this. We're doing peer-to-peer learning sessions, and those will be coming up, and we're going to start those in New Mexico and then branch them out to other parts of in the region. And then we're doing training and funding for technical manager and financial capacity building. So that's what this is today. So we're doing a training on wastewater math to help you all get to the point where you can both have a better math understanding for certification exams, but most importantly, to better utilize these concepts for your processes at your plant. So hopefully it is helpful content that we will be going over today. Okay, so like I said, this is part of a series. So today we are on session 2 of our series. We're going to be doing them every 4 weeks, all the way until next fall, next summer about. And this one we're going to do an introduction to wastewater math, and then please join us next month for collection systems and mechanical systems. And these are with various staff members at the Southwest Environmental Finance Center. Okay, so just some last logistics before we get going. We have not submitted this for pre-approval for continuing education credits. For continuing education credits for like CEUs, but we will be issuing a certificate at the end, so you can submit it to your certifying agency to accept if you need these continuing education credits. We'll also email out these slides a day or two after the webinar, so you have them as a resource. And we'll also send out the recording too. We'll post these online and then you can review these recordings. So we'll send that out as well. And like I said, we'll send out certificates at the end after the series is done. And also, lastly, there will be a review at the end of the webinar or an evaluation. So please fill that out and let us know how we did. Our goal is to design these so they're most beneficial for you all. So please let us know what you liked, what you didn't like, and what we can do better for our next session. And then lastly, please let us know who you are in the chat. It's great to hear where people are coming from. A lot of times you are all your best resource. So it's great to know the other people involved in this industry, and it's great for us to know who you're with and or where you're with it, but also who you're attending with. If there's anyone else attending with you, please let us know so we can count that as well. Okay, so today's agenda, we're going to go over unit conversions, then we're going to go over the Davidson pie wheel, which AJ is going to cover. Then we're going to go into volume, velocity, flow, detention time, concentrations, percent removal. So a lot of these concepts are going to build upon each other. Um, and no matter what level of math proficiency you're at, I think you'll find some benefit and some you'll learn something today. Um, so we'll start going over these, and please throughout let us know if you have any questions. Okay, so this is a math training, so of course we'll do some all together, and then I'll have you all fill out or do some of these questions on your own. So I want to show you all how to do these and give an example, but really the best way to learn these is by doing them. Doing the problems yourselves, and then we'll have multiple choice, just a poll like we just had, and then you can enter your answer as that poll. But no worries if you don't get it right. And no worries also if you're not done in time. Don't feel like I don't want to, there's no pressure on filling out the correct answer or an answer at all if you're not there in time. Because of course we have a whole range of math ability here. So some of you will be really quick, some people might be slower, and that's totally fine. So the whole purpose of this is for you to get something out of this. Um, and so um, we'll go at a decent pace, but we'll try to keep it going so we get through a decent amount of content, but don't want to lose anybody. But if you want to review it, you can always review it online, and we'll send out these slides. Okay, so for doing this, you will need a calculator and then a pencil and some paper to do some calculations. And your phone calculator is going to be just fine. But of course, if you take the exam, the certification exam, you won't be able to use your phone. So sometimes it's nice to practice on just a basic calculator. Okay. Okay, now to get going with the content, here's the fun part. Okay, so first we're going to start with unit conversions. So these are a lot of the standard ones in the water and wastewater industry. So some of these are basic that you do all the time, of course. So time, like seconds to minutes to hours to days. We're going to do lengths, so inches to feet, feet to miles. Volumes, that's a big one. Like volumes for storage tanks, really any kind of thing that holds water or wastewater. A lot of times you need to convert that to gallons or cubic feet, or millions of gallons. Flow, so millions of gallons per day, gallons per minute. We need to go back and forth between those a lot. Percent solution strength to a decimal percent. A lot of times your chemicals come as maybe 12% chlorine. So sometimes you need to convert that into like what part per million that is when you add it to a stream. And there's so many more. So we're just touching on a few of them. Okay, and so throughout this training today, I'm going to go over some like basic concepts too, because I don't want you all just to know what this formula is. I want you to kind of understand how those work and why we're doing what we're doing, because I think that makes things stick a little bit better in my head at least. Okay, so thinking about that, what is a conversion factor? So a conversion factor, it is a numerical relationship used to multiply or divide a quantity when converting from one system of units to another. So what does that really mean though? So it means that you're going from one of these things, like on the left, there's this column that's an acre foot, and then you can go to the different units. Um, so this is the table from the ABC, the Association of Boards of Certification. So this is on the formula sheet that you get when you're taking the certification exam. And so it has all of these different conversion factors. So if you want to go from miles to feet or anything you want to do, you can just use one of these numbers and you either divide or multiply that. But what are you actually doing and how do you know whether you divide or you multiply? Okay, so you're multiplying your measurement by the conversion factor, but what are you really doing? So these conversion factors, they you can really think of them as a fraction. So, and then you're multiplying them by 1. So these turn into 1 because in this example, so down here, my conversion factor is 1 gallon equals 3.79 liters. So those are the same thing. So if I have a gallon jug of milk, that's 1 gallon, or it's 3.79 liters. It's the same thing. So if we put that into a fraction, 1 gallon over 3.79, if we divide that, because 1 divided by 1 equals 1. So it's the same thing. So we can do it with the 1 gallon on top and the 3.79 on the bottom, or we can flip it around. We can do it the other way because they really are the same thing. And so when we're using a conversion factor, what we're really doing is we're multiplying whatever our measurement is, and we're multiplying that by 1. But because because of that conversion factor, we're changing the units. We're not changing the value. It's still my 1 gallon of milk. But now we can just write it down as 3.79 liters as opposed to 1 gallon. Well, we're not changing the value. Okay, so we're going to do an example together. So your sodium hypochlorite tank holds 40 gallons, but the store sells it by the liter. So how many liters of sodium hypochlorite do you need to fill up your 40-gallon tank? Okay, so what are we asking in this question? So I'm just going to start out by writing down my conversion factor because we are going from gallons into liters because we need to buy an X number of liters of this chemical. And so I'm going to write down my conversion factor right here. And then I'm going to set up my equation. So I'm going to multiply 40 times my conversion factor. And I'm going to have the 3.79 liters on the top as my numerator, and then the 1 gallon on the bottom as my denominator, because I want to cancel those out. I want to cancel out gallons because gallon is on top of the equation and the bottom of the equation, and then we're left with liters. And so we need to buy about 150 liters. So in this example, I wrote out this with the multiplication sign in parentheses, but some of you might be familiar with this grid way of writing things down. So it's the same thing. So I'm just going to do the same thing. I have 40 gallons over here. And then if there's no numerator on something, we can have just a 1 as a default value as a numerator. And then over here, we're multiplying it by the conversion factor. And so then we get the same answer. We cancel out our gallons and we get about 150 liters. All right, let's see. Yes, okay. Sorry, let me make somebody a co-host really quick. My apologies. Okay. Sorry for the delay. I had to do technical things. Okay, so now it's y'all's turn. So now we're going to do a unit conversion, and we're going to start with one that's pretty simple. One you probably do a lot in your head anyway, going from or just kind of having a basic understanding of what converting time from hours into days and minutes and so on. So our first one, a pump runs for 11.25 hours per day. So I want to figure out how many minutes does it run per day on average. Okay, so our options are 5 minutes, 270 minutes, 675 minutes, 1,000 or 16,200 minutes per day. So I'm going to launch that poll. Okay. Okay. All right. So fill in that poll question when you have the answer, and then we'll go over it. So how many minutes in a day does this run? I'll give you all about another minute or so. And if you're having problems with the poll, feel free to put your answer in the chat. Okay, it looks like most people have answered, so I'm going to end this poll. And if you're not done yet, that's totally fine. You can go back and look at the answers with the slides when we send them out, or you can watch the video. So I'm going to end this poll now. Okay. And so almost everybody said 675 minutes. Okay. So let's see. Let's see what I got. And it's possible that I missed I got something wrong throughout some of these. So please let me know if you ever find an error in my math. Okay, so I'm going to cancel out those hours because there's 1 hour on top, 1 hour unit on bottom. Then we're going to multiply across, and that ends up being 675 minutes per day is how many minutes that pump is running. So great job. Pretty much everybody got that one right. All right, we're just going to do another conversion here, and this one is pretty similar. We're just going to do something a little bit different. So this one we're trying to figure out what we're converting length. So you're trying to determine the volume of 1,000 feet of 8-inch pipe. The first thing you want to do is make your units match. How many feet in diameter is the 8-inch pipe? And I think I wrote that kind of weird, but what we want to do is convert that 8 inches into feet. And in this problem, I put this extra information in there that you don't need, which will happen on the certification exam. So we don't care how long the feet is. We're just trying to figure out what that diameter is. Okay, so let me pull up that poll. This is poll 2. Okay. Give you about a minute. Okay. Looks like most people have answered. So I'm going to end this poll. Okay, and share these results. Okay, so it looks like most people said A, 0.67 feet. Okay, so let's go through and see what I got. Well, I guess I hadn't put those up on here yet, but those should have came up in the poll, the multiple choices. Okay, so I just want to convert 8 inches into feet. So I set up my little grid, my little equation here, and my inches, these units cross out because one's in the denominator, one's in the numerator, and then cross those out, and then multiply across, and we get 0.67 feet. So to do this, we would divide 8 divided by 12. So good job. Most people got this right. Awesome. Okay. And I think I'm gonna skip this one just for the sake of time. There's one more conversion problem, but I think I'm gonna keep going to get to some other content. So now we've talked about conversion factors, and this is really crucial for getting everything in the right units to set up your equation. So a lot of these equations are now going to be in that ABC formula sheet, but in order to put what they give to you in there, a lot of times you have to do a conversion factor to start with. Sometimes you have to do it at the end. So that's a basic step along the way. And so now I'm going to move on to pass the microphone to AJ, and AJ is going to talk about these Davidson pie wheels, which um, for me, these are really great for some people. Um, People's brains click with these and they understand them. I personally don't like using them. I feel like for me, I like writing out the equation a lot better. But these are a great visualization. So and AJ understands them better than I do. So thank you, AJ, for going over these.
Yeah, no problem. And I wouldn't say I understand them better. I just know that I have seen many people who do like them. I'm kind of more on Tucker's train as well. I like to use conversion factors, but Davidson Pi wheels are another tool that are included in many certification tests or in your equation sheets that can be used to also like simplify equations and understand the kind of equations that you may be using. So, like I said, many of the wastewater and water certification tests or classes provide this kind of visual tool to take your complex equations and create a simple format of them. So, the way the Davidson pie wheel works is that the circle is divided into sections that represent the different variables that are used in your wastewater and water equations to figure out different outcomes that you may be given in like a word problem or in just like a basic equation in general. Now, the variables on the bottom of the pie wheel are multiplied together to calculate the value of the variable in the top half of the pie wheel. So what that means is whatever is on the top of the pie wheel in the top half is equal to the bottom sections multiplied by each other. So the way you'd set up that equation would be like the top, which is what you're trying to find in an equation, would be either on the left or right side of the equation, and the other three would be on the other side. The top half is equal to the product of those. And then interchangeably, by dividing the values at the top of the pie by any of the variables in the bottom, you would get the values for the other variables that you did not use in that division problem. And we'll kind of explain how to do that on the next couple slides. So we'll go over an example how to do this. It's pretty straightforward. We're just using kind of basic arithmetic and multiplying. So our first example, we're going to calculate the area of a triangle that was measured to have a base of 10 inches and a height of 6 inches. And we're going to do this based on our Davidson pie wheel. So as you can see, like I said, in this pie, in the top half is the area of a triangle. And in the bottom, we have B, which is going to be our base, and H, which is equal to our height. So one thing to point out when using the Davidson pie wheels is you do have to kind of sometimes recognize when some of our variables are given as just a symbol. So base is B, height is H, and then you also multiply the base and the height times 1/2. We'll show you how to do that here. So we take for that circle, for that first pie, we can replace the B with an H, You don't always have to do this. This is just to kind of show for our example. So the area of the triangle we have in our top half, then we have 10 inches as our base, 6 inches as our height, and we keep 1/2. And then we can take those and form an equation out of them. So, like we said, the top half is equal to the 10 inches times the 6 inches times the 1/2, aka the top half of the pie is equal to the six sections of the, or I'm sorry, the three sections of the pie on the bottom half. And so we would multiply those together to equal 30 inches squared. So let's go ahead and practice that on our second pie wheel. I'm sorry. No, this is what we were talking about with our inverse. This is going to be how to use the bottom variables, and we can divide our top variable by those bottom variables to equal one of the variables on the bottom. So for this example, to achieve the proper detention time, an activated sludge plant is required to have a rectangular sludge basin with a volume of 168 cubic feet. So we're given the variable at the top already, the volume of a rectangular tank, and then it has been determined that the space available to house the tank has a length of 7 feet and a width of 8 feet. And the question is asking what height is needed to provide the desired tank volume. So we take our Davidson pinwheel and we can replace the variables that we know. So we have replaced the volume of a rectangular tank with 168 cubic feet. And then we also replaced the length with 7 feet, which was represented by L, and the width with 8 feet, which was represented by W. And that only leaves us with the only remaining variable is our height. So that's what the question is asking. What height is needed to provide the desired tank? So we plug those into our equation because the tank height was multiplied, would normally be multiplied by 7 feet and 8 feet. We move those to the other side of the equation, and then we have a tank volume of 168 cubic feet divided by the product of 7 feet and 8 feet, which is equal to 3 feet. So that's how we use it to kind of find the variables on the bottom as well. We divide the top by the ones that we do know, giving us the h, or the height. So those are just some of the examples of that. And we just kind of want to mention that these are both tools that many people find useful in solving wastewater and water math. So for the conversion factors, by organizing using our conversion factors, it helps simplify our complex equations. This is done by reducing or by canceling out units and being able to make sure we're verifying our correct units are in our result. So that helps reduce our calculation errors. Now for the Davidson pie wheels, this also simplifies complex equations by just taking a nice little pie wheel and understanding where to find the desired product or the variables that are used to calculate that product. This helps you kind of increase your efficiency of those calculations. You can do it kind of quickly. Then it also provides an additional tool to ensure the accuracy. So if you're someone that likes to just use conversion factors or to multiply across and to kind of just understand the equation in like a detailed way, you can calculate that way that you're comfortable with and then use the Davidson pie wheel to supplement a quick way to see that you verified to verify your answer. And I'm going to go ahead and pass it back to Tucker, and he's going to go on with some more complex concepts.
Thank you, AJ. Yeah, so if you're comfortable using those Davidson pie wheels, then that's great. With math, a lot of our brains work different ways of what makes most sense to us. And so I'm not going to be going through, these examples, I'm not going to be using the Davidson pie wheels, but feel free to do that if you want to calculate it on your own, if you want to use that. So I encourage you to do whatever makes the most sense in your head. And as we're going throughout this too, there's going to be a few other things that are going to be give you a few different ways to calculate things. So When it comes to math, always do what you're comfortable with, because a lot of times there's multiple ways to do things. Okay, so first we're just going to talk about volumes because this really is the basis of water and wastewater, because we're dealing with fluid substances, so they always take the shape of their container. So this is for all kinds of different things, tanks, pipes, clarifiers, lagoons. Those are things that we would have water and wastewater in, but also things for excavation. So say you need to lay some new pipe, and you need to order some fill dirt. How many cubic yards do you need to fill that in? So really volumes is really the basis of a lot of these concepts. So we're going to start with volumes, and then we're going to go into some other things that incorporate volumes. Okay, so really quick, how do we calculate the volume of a container? Um, oh, oops, a poll just popped up. It did for me at least. Okay, so my apologies. Okay, so thinking about volumes and how we calculate those, we're really just going to start with the formula for the area of a rectangle and the area of a circle. So the only thing we do to turn these into volumes is we just make them three-dimensional. So here's our rectangle and our circle, and we're just going to make those flat. And then we're going to add the third dimension to them. So with a rectangle, we're adding rectangle upon rectangle and upon rectangle. So you can think of these as maybe 1 feet, 2 feet, 3 feet going up. And then the same thing for the circle. So we're just adding stacks of circles on top of each other. And so maybe think of this 1 foot, 2 foot, 3 foot, 4 foot, and that's going to be our height. And so then when we have these formulas, it's just length times width times height, and then pi times the radius squared times the height. So we're going to use these to calculate a few things. The first thing we're going to do is that rectangle, so a three-dimensional rectangle into a box. So as an example, we have our height, our width, and our length. Height of 4 feet, width of 12 feet, length of 24 feet. So in our example from the ABC formula sheet, we have all those length times width times height equals volume. So I'm just going to plug those in. So 24 times 12 times 4. If I put that into my calculator, I come up with 1,152 cubic feet. So pretty simple there. And so now I'm going to let you all do one. So in this first question for volumes, so find the volume of fill dirt in cubic feet needed to replace an excavation that is 60 feet long, 3 feet wide, and 40 feet deep. All right, so I'll put up that poll. So fill in this poll question when you're ready. I'll give you about another 30 seconds. Okay, I'm going to end this poll in 10 seconds. So put it in your answer now if you haven't. Okay. All right, and pretty much everybody said C, 720 feet. So nice job. All right, so I'm going to stop sharing that one and we're going to go over this. Okay, so So first I wrote down my formula. So that's where I start with all of these is I always write down my formula and then I just plug in the values for those. So 60 feet times 3 feet times 4 feet. If we plug that into our calculator and multiply that out, 720 feet. Cubic feet, I should say. So you keep have your right units on there. So cubic feet, because we're talking about volume. So we're in 3 dimensions right here. So we have cubic feet. So the answer is C, of course. So nice job. Pretty much everyone got that. Okay, and now we're just going from a box to a cylinder. So this isn't one of the ones that, like I mentioned, there's a few different ways to do some things. In your ABC formula sheet, you'll find two different equations for the area of a circle, and thus you also have two different formulas for the volume of a cylinder. So you have pi times the radius squared times height, or you have 0.785 times the diameter squared times height. So use whatever of these you're most comfortable with. When I was in school, I learned pi r squared times height. So I'm going to use that one in these examples. Whichever one you use, you're going to find the same answer. Okay, so here's a cylinder, and we can think of this as a storage tank or really anything that comes in a cylinder, like a barrel of chemicals or whatever. So in this example, we have a height of 32 feet and a diameter of 20 feet. And so the radius is half of the diameter. So 20 divided by 2 is 10. And so that's what I'm going to use for my equation. So I'm just going to first write down my equation, pi times r squared times height, and then plug in my numbers. So I'm just going to use 3.14 times 4 pi. You might have a pi button on your calculator, so feel free to use that. That's going to end up in an answer that's probably more precise, more accurate than if you round to 3.14. But really 3.14 is plenty good enough for these calculations, for this and for the exam. Okay, and then I'm going to put in my radius as 10 feet into the equation and the height. And so I'm going to calculate this out, but what I need to do first is I need to remember my order of operations. So exponent is going to be come sooner in my order of operations multiplication. So first I need to square that 10 feet. So I need to multiply 10 feet times 10 feet. And so that's going to give me 100 feet squared. And so we started out with just 10 feet, which is just the length or just the one dimension, but now we're multiplying that by itself. And so now we're going to have feet squared. So now we're in 2 dimensions. So we have that feet squared. Okay, and then now that we have that, we have 3.14 times 100 feet squared times 32 feet. We can plug that all into our calculator, and we're going to end up with 10,048 feet cubed. And so now we're in 3 dimensions, so we have cubic feet. And so a lot of times though, you come to your answer in cubic feet, but really gallons is more useful for what we're doing a lot of the time. So let's convert that one to gallons using our conversion factor. So from that formula sheet, I know 1 cubic foot of water equals 7.48 gallons. So I'm going to multiply that. I'm going to turn that conversion factor into a fraction, and I have feet cubed as the numerator on this side, and so I want to have it on or denominator on this side. So I want to have it on the bottom over here. And so I want to cancel those out, feet cubed, and then if we multiply that through, we end up with gallons. Okay, so our answer is 75,159 gallons. So that's a pretty specific answer. So we have that 9 in that as that last unit. We really don't know if there is like 9 gallons in there versus 10, because so say you pour another gallon of water in your storage tank that's 32 feet high. Are you really going to have a measurable difference? Probably not. So we're going to round that to 75,000 gallons. And this is related to significant figures. So maybe some of you have heard that term before. So in this example, I'm going to have 2 significant figures, 7 and 5. So 2 significant figures. And then I'm going to round the rest, just because that's how accurate we are. That's how accurate we started with. We had 2 units of measurement. So we're just going to end with 2 units of measurement. And I did hear a joke the other day that I thought was kind of funny, and it was a good example of why significant figures kind of are important. So a family goes to a museum and they're looking at a dinosaur skeleton. And they asked a security guard standing there, "How old is that dinosaur skeleton?" And the security guard says, "It's 700, or excuse me, it's 7,000,005 years old." They said, "Oh my gosh, that's so specific. How do you know it's 7,000,005 years old?" And the security guard says, "Well, when I started, somebody told me that it was 70 million years old, and I've worked here for 5 years." So I thought that's pretty funny because, of course, we don't know that that specific skeleton is 7,000,005 years old. We would still say it's 7 million years old because that's a lot bigger value, and that five is pretty insignificant. So it's kind of that same concept when we're measuring things in water and wastewater because sometimes we're not that accurate in our measurements. So we're just going to round up or round down. Okay. So now I'm going to turn it over to you all. So now here's another multiple choice question for you all. So here's a storage tank. This is a drinking water storage tank, but it's the same concept for all kinds of wastewater things. This could easily be a clarifier or anything. So we want to know what is the volume in cubic feet for a tank that is 15 feet tall, has a diameter of 18 feet. And then we want to know what that volume is in gallons. Okay, so here's my units over here. So I'm gonna have height of 15 feet, diameter of 18, which then means that my radius is 9 feet. So we're gonna have multiple choice here, and I'm gonna put up this poll, and this one has two answers, one for cubic feet and one for gallons. So I'm gonna launch this poll. Okay, so there's two answers or two questions in here. So um, answer these when you've done your calculation. I'll give you a few minutes. And as we're going through, if you have any questions about the specific problems or equations or anything, please put them in the chat. You can chat with everybody if you want, or you can send them specifically to me or AJ. But generally, if you have a question about something, if something doesn't make sense, probably other people will as well. So it's good to just ask as a group, and then we can answer for everybody. And because this is a bit of a longer calculation than the other ones we did, I'm going to start just going through it. So if you need help with the calculations, um, look at your screen and they'll pop up. Okay, so almost the whole thing's up there now. So you should be able to at least get the first question right. So put in your answer when you're ready. I'll give you about 30 more seconds. Okay, I'll give you about 10 more seconds, so put in your answer now if you're about there. And this poll. Okay, so if you look at these answers, looks like most people said B, so 3,815 feet. So that's great. And then for the second part, what is that volume in gallons? So we're going to convert that cubic feet into gallons, and we come out with 29,000. So good job, everybody. Most people got that. Awesome job. And if you didn't get that, then that's totally fine. The example is here, and I'm going to go through it more. So just 1 second. I'll stop sharing those. Okay, so I already started going through this one. So pretty much all that I did is put those numbers into my formula. So 3.14 times 9 feet, and then have that whole thing squared, times 15 feet, which is our height. So first thing I'm going to do is I'm going to square that 9 feet, which turns it into 81 feet squared, and then multiply all those through, and then we come out with 3,815 cubic feet. And then we want to convert that to gallons. So we're just going to use our conversion factor, 7.48 gallons per cubic foot. So I'm going to multiply those out and cancel my units. And so if we plug those into our calculator, we come out with 28,536 gallons. And we're going to round that up to 29,000 gallons. So a lot of times in your certification exams, there will be rounded answers too. So just if you get your answer close to what is on there, select that one because that one's probably the right one. And sometimes you may have rounded sometime during your calculation. So sometimes you'll end up with slightly different answer. And then it might be slightly different even rounded. So if you have an answer that's generally close to one that's in the answer, one of the four selections, usually go with that one. Okay, so good job, everybody. If you have any questions, then feel free to put it in the chat. Okay, and maybe we'll go over one more concept and then we'll take a 5-minute break. Okay, so now we're going to move into a different concept, but it still isn't going to incorporate volume because kind of what we're doing right now is we're building on some of the stuff we've already gone over. Okay, so we're going to talk about velocity, what that is, and how it differs from flow rates. So velocity, that's how fast your water is moving through a pipe at a given time. So it's a distance traveled per unit of time. And this is the same thing as when you're driving your car, how many miles per hour you're going. It's just a length over a period of time. So a lot of times in water and wastewater, we're going to have feet per second is what that unit is going to be. Sometimes maybe even have it as meters per second, but usually in the US, because we use the imperial system, we'll stick to feet for this generally. Okay, and how does that differ from flow? So flow is related, but it's a different concept. So instead of a distance, so 2 dimensions, we're going to add that third dimension. And so now it's going to be a volume per time. So a volume per time is going to be something like gallons per minute, cubic feet per second, or million gallons per day. And of course, these are related. And so there's a formula that can go back and forth between the two. So our velocity formula from our ABC formula sheet up here is the flow rate in cubic feet per second divided by area. Or you can also measure velocity simply by doing distance over time, which is what even the units are. It's a distance, feet, over time. And then so because velocity and flow rate are related, there's the similar formula for flow rate. So it's just a rearranged equation. So flow rate in feet per second is the area. So that's usually be the area of your pipe. So you're going to have like the area of your 8-inch diameter pipe, and then multiplied by the velocity. So how fast that water is moving through that pipe. Okay, and usually, like I said, velocity is going to be feet per second, where flow is going to be cubic feet per second. Okay, so I'm going to have you all do one of these. So this one, okay, we got a rubber ducky and we put it in a pipe. And so it's flowing through that pipe that is 520 feet long. It comes out at the end in 142 seconds. So we want to know how fast is water flowing through that pipe, assuming that the water and the ducky are moving through the pipe at the same speed. Okay, so I'm going to launch this hole. And so this one is just plug and play. So you can just put the numbers into that formula and you should come up with the answer. Okay. Okay, so I just launched that poll. So fill this in when you have your answer. I give you about 30 more seconds for this one. Okay, so I'm going to end this poll, share the results. It looks like most people said D, 3.7 feet per second. All right. So great job. We're going to go through that. And if you didn't get that right question, no worries. Hopefully it makes sense as we go through it. Okay. So already I wrote down my equation. So that's the first thing I wanted to do is velocity equals distance over time. And then I just plugged in my values, 520 feet divided by 142 seconds. And I plugged that into my calculator and I came out with 3.7 feet per second. So our answer is going to be D. So great job. Most of you got that. Okay, so we're going to continue with now we're going from velocity, now we're going to flow. So a bit different concept, but it is related. So we're going to do one question like this, and then we're going back to our ducky. So we're going to see how the ducky flows through a pipe. So okay. Okay, so flow, it is also a measurement over time, but now we're talking about a volume over time instead of a distance over time. So, and this is something that you can do very, very simply. So in this question, you want to figure out the capacity of your service pump. So you start the pump and you just start filling up 5 gallon buckets and you have your stopwatch on your watch and you just figure out how many buckets can I fill up in 1 minute. And you fill up 8 whole buckets in 1 minute. So what is the capacity of your pump in gallons per minute? Okay, and this is a multiple choice, so I'm going to launch this poll, and this also give us a gauge on how many people are back from our break. Okay. Okay, and this exact example, I did this recently to figure out how much water I was out of town, and my next door neighbor was watering my plants, and he left the sprinkler on for about a day. So I did this little calculation to figure out how much water he wasted watering my plants for a whole day. Talk about inefficiency. Okay, got a lot of answers so far. I'll give you about 10 more seconds because it seems a lot of people have answered already. Okay, I'm going to end this poll, share those results. Okay, so almost everybody said 40 gallons per minute. So great job. I'm going to stop sharing. Okay, so going to do the math here really quick. So our flow is volume over time. So I'm going to start out by writing down my equation, and then I'm simply going to plug in my numbers to that. So the volume, so I filled up 8 buckets, and they're 5-gallon buckets. So 8 times 5, and then my time is going to be 1 minute. So if we plug that in, 40 gallons divided by 1 minute. So 40 gallons per minute. So yep, the answer is B. So great job. And then if you're doing something like this, of course, you probably, I don't know, having 8 5-gallon buckets is quite a bit. So it'd probably be easier to just time how long it takes for you to fill up one 5-gallon bucket. And then you can do that and you can plug that exact same thing into here. So you just do 5 gallons divided by however much time that was, and you can get the same calculation, and you don't need 8 buckets to do this. Okay. So sometimes wastewater and water math, it seems fancy, but sometimes you can do the math with a bucket. Okay, so here's another one. We're going back to our ducky. So now we're going to calculate this a little different. We're going to go from flow, or excuse me, we're going to go from volume to flow in our calculation. So we have our same ducky, but this time we're going to have it going through a 18-inch diameter pipe that's full. And so we want to know what the flow is when our ducky is moving through our pipe at 2.5 feet per second. So what is the flow? Okay, so I'm going to, oh no, sorry, this is an example question. This isn't one you're doing. My apologies. You'll do the same one in a second, but I want to go over an example really quick. Okay, so we're going to start out by writing down the equation. That's how I always like to start. So my flow is my velocity times my area, and that's from that formula sheet, which is down, I just copied and pasted it from that formula sheet at the bottom here. So our flow rate in cubic feet per second is area in square feet multiplied by velocity in feet per second. Okay, so first I need to figure out area because that's half of our equation. So we need to figure out the area. So I wrote down my equation for that to start out with. So pi times the root squared. Then I'm going to plug my numbers in. So I'm going to use radius as opposed to diameter. And so I guess first I had to figure out what that diameter was in feet, and then put that in half. So our diameter is 18 inches, and then I want to figure out what that is in feet. So I divided that by 12, and so it's 1.5, so it's a 1.5 feet. And then my radius is, of course, half of that. So half of a 1.5 feet is 0.75 feet. So it's 3/4 of a foot is the radius. So that's what I'm going to use in my equation. And then I'm going to start calculating that out. So of course I have to do those exponents first. So I'm going to multiply 0.75 feet times 0.75 feet. And that comes out to 0.56 feet squared. And then we're going to multiply that out. And we come up with 1.77 square feet. So that's going to be the surface area of the end of that pipe. If we're looking at the pipe, looking like into the pipe, that's the area of that opening. Okay, so now we have our area. So now we can plug that into our flow equation. So our velocity is 2.5 feet per second, and that was given to us in the question. And now we have our area, 1.77 feet squared. And then so we're going to just multiply that out, and that comes to 4.42 cubic feet per second. So there's our flow right there. So we're almost done because we've calculated it now in cubic feet per second, but we want to change that to gallons per minute because that's what our question is asking us, and that's usually a more useful unit to have flow in. Okay, so there's our conversion factors right there, and those are also from that formula sheet. I don't know if it says 60 seconds in a minute, but I bet everybody knows that. Okay, so I'm going to set up my grid here. So I'm going to use this grid, and I'm just going to put that my first part of that down. That's my actual flow. So I'm going to have 4.42 cubic feet, and that's on the top as my denominator. And that's our flow per second. And then I'm going to put the first conversion factor in there. So that's going to be converting that from cubic feet into gallons. So I want to get rid of my cubic feet. So I want to put that cubic feet unit on the bottom so I can cross those out and have gallons on top. And then I'm just going to also put my other conversion factor in there. So I want to have seconds on top because I want to cancel out the seconds in um, in my flow in that first unit. So I'm just going to calculate those out and cross out my units. So if something's on top and the bottom, I can cross those out. So I'll cross out feet cubed and I'll cross out seconds. And then that leaves me with gallons per minute. And so I times 4.42 times 7.48 times 60, and I end up with 1,984 gallons per minute. Nice and simple, right? Okay, hopefully that all made sense though. And so now we're going to move on to one that's pretty much the exact same question, but I want you all to do this one. So it's the same question, but with some different values. So if you calculated that one out, you should be able to calculate this one out too using the same methodology. So this one, we want to know what the flow is in gallons per minute. And it's going to be a 12-inch pipe this time, 12-inch diameter. And our rubber ducky is cruising through at a velocity of 1.1 feet per second. Okay, so I'll give you all a few minutes to figure that out. And I'm going to launch this poll. So fill this in when you have your answer. I'm just going to start clicking through these. So if you're stuck, hopefully this will help you.
Oh, it's nice to meet him.
I have.
Okay, I'll give you about 30 more seconds or so. So pretty much everything's up there except for the conversion. So if you've gotten stuck, take a peek at the screen and hopefully it'll get you in the right direction. Now I'm going to close this poll in about 5 seconds. So put in your answer if you haven't yet. I'm going to end this poll and share the results. All right, so if we look at these results, you should have them on your screen now. Looks like most people did put, or about half of the people put A, 388 gallons per minute. But quite a few people also said 775. So let's go through and let's calculate it out. Okay, so I already have most of this up here. So if you look kind of on the right of this or rectangle, we start out with figuring out the area. So I have pi times the radius squared. I'm going to plug in my radius there, which is half a foot, because our diameter is 12 inches, which of course is 1 foot. So half that is the radius. Then multiplying 0.5 feet times 0.5 feet gets me to 0.25 feet squared. I multiply that by pi, and we get an area of 0.785 square feet. And so that's the area that we're going to put into our flow equation. So our flow equals velocity multiplied by area. So our velocity, it gives us at 1.1 feet per second, and then we'll multiply that by our area. And if we plug that into our calculator, we get 0.86 cubic feet per second. So that is our flow, but we need to then convert it into gallons per minute. And so our conversion factors are right here. So 7.48 gallons per cubic foot, and then 60 seconds is a minute. So I set up my grid down here. So I have my flow right there as our first part of this grid. And then I have our conversion factor for going from cubic feet to gallons. And then right here, I have our conversion factor going from seconds to minutes. And then I can cross out my units. So I cross out our cubic feet because we have one on the top and one on the bottom. And then I crossed out seconds. And then if we multiply those through, we get 388 gallons per minute. So good job, everybody. And hopefully that makes sense. If that doesn't make sense, hopefully the math clarifies things. But if you have any questions, please put them in the chat. So happy to explain things better. Sometimes I don't explain things that well. So so let me know if you have a question. If you have a question, probably other people do too. Okay. Okay, so we're gonna go next to another concept called detention time, and this is related to a lot of the things we've gone over before, flow and velocity. So what is detention time? Detention time, and I also heard it called retention time. So it's basically just the amount of time that water is in any given vessel. So water is constantly flowing through our plants. It's coming in and then it's being discharged. And this is whether we're wastewater, drinking water, all kinds of different things and different kind of chambers. Um, so detention time, I said it was related to volume and flow, and that's literally what it is. So it's the volume divided by the flow. And so this formula down here at the bottom of the screen, this is directly copied and pasted from the ABC formula sheet. And so that's how we calculate these. So I'm going to do an example right here. And so there's all kinds of different, I think, um, you would use this in a plant a lot of times, but even like for a lagoon, you would want to figure this out. How long is your water in your lagoon before it's being discharged? So here's a lagoon that on our left. And so it's a rectangular wastewater lagoon that is continuously discharging. And so the water's flowing in one side and flowing out the other side. And so this lagoon is 200 feet long, 100 feet wide, and its depth is 8 feet. And so um, we want to figure out what is detention time if our average flow is 0.6 million gallons per day. So this could be in all kinds of different units, but a lot of times our plants are designed in million gallons per day. So that's what we're going to start with. Um, so going through here, I'm going to start doing this calculation. So first, we need to figure out what the volume is because this is the first part of our detention time equation. So to figure out our volume, again, it is length times width times height. So I'm just going to plug in my values there. So 200 feet times 100 feet times 8 feet. And that's going to calculate to 160,000 cubic feet. And so that's a pretty big number. Sometimes it's hard to kind of wrap our heads around that. So maybe we'll calculate that, convert that into gallons, because that's usually what we use for volumes it's a little more useful. So we're going to use our conversion factor. So we're going to convert 160,000 cubic feet into gallons. So there's our conversion factor there. We're going to cross out our cubic feet and we're left with gallons. And so now we're left with 1,196,800 gallons. So that's even a bigger number. So kind of hard to wrap your head around potentially how these numbers get pretty big. So because of that, we're going to convert it into million gallons. So we're going to use another conversion factor. And that conversion factor is just a million. So we're just going to move the decimal place 6 places because we have 6 zeros. And so if you want to do this on your calculator, you would plug in 1,196,800 divided by 1 million. And so then we're going to end up with 1.1968 million gallons. Okay, so there is our volume. And so we wanted it to be in million gallons because in our question, it gives us our average flow of 0.6 million gallons per day. So we had to have that in million gallons, so those units will cancel out. If our question gave the flow in like gallons per day or cubic feet per day, we wouldn't have had to do those conversions. But we need to make sure our units are compatible so we can cancel those out. So now we have our units compatible. I'm going to plug those into that equation. So our detention time is our volume, which we just calculated as 1.1968 million gallons, divided by 0.6 million gallons per day. And so we're going to cross out those million gallons, and then we end up with 2 days. So on average, your water flows into your lagoon, and then it's there for 2 days, and then it flows out the end. And this is useful on wastewater, but a lot of times in drinking water, you have to have that CT value requirement for contact time for the chlorine to react with your drinking water. So this is something you calculate quite a bit. So it's very applicable equation. So now I'm going to have you all calculate this out. And so in this example, in this question, so your clarifier is 40 feet in diameter and 25 feet deep. Your average flow is 1.2 million gallons per day. So what is the detention time in your clarifier in days? And then we want to convert that into hours because sometimes you want to know what that value is in hours because that's a more applicable unit. So I'm going to have you calculate this all out. It's going to be the exact same as the last one we just did together, but instead it's going to be a cylinder as opposed to like a rectangle as the vessel because now we're going to have a clarifier as opposed to a lagoon. Okay, so I'm going to launch that poll. Give people a few minutes. And if you're stuck, I'm starting to go through the calculations on the screen. So take a peek if you want some guidance. Okay, so all the calculations and the answer for the first part are up there. I'll give you about one more minute. Okay, it looks like just over half the people have answered, so um, quite a bit. So put in your answer now if you haven't. I'm going to close in about 5 seconds. Okay, I'm going to end this poll. Share the results. Okay, it looks like most people put 0.2 days. Great. That's what I had too. And then 4.8 hours. So that's what most people had. So let's go through that. Okay, so I already have this mostly on the screen. But first, what I wanted to do is I calculated the volume of this clarifier. So this is a cylinder. So I did pi times the radius squared times height. So I plugged those in, and first I figured out what that radius squared was. So multiplied 20 feet by 20 feet, which got me to 400 feet squared. Then calculated that out, and then ended up with a volume of 31,400 cubic feet. And then I wanted to convert that to gallons. So I used my conversion factor of 7.48 gallons per cubic foot. We crossed out our cubic feet and then multiplied that through, and we came out with 234,872 gallons. And then the next step was to convert this to million gallons. And so to make it into a million gallons, what we want to just do is divide by a million, which also just means that we're moving our decimal point 6 places. Because we have 6 zeros, so we're moving it decimal 6 places to the left. So you end up with 0.235 million gallons. And then the last thing we want to do is calculate that detention time by dividing it by our flow. So we divide 0.235 million gallons divided by 1.2 million gallons per day, and we end up with 0.2 days. And it's kind of not super intuitive to know what 0.2 days is, because we usually think of the day in hours. So how many hours is that? So I'm going to convert that. So I'm going to multiply that by 24 hours in a day. Then we cross out our day units and we end up with hours. So it's going to be 4.8 hours. So that's a lot easier time to visualize. Okay, so our answers were B and B. So great job. Most people got that. Okay. So now we're going to move on to another concept, and this one's a little bit different. We're not going to use like the volumes and flow quite as much with this concept. So Now we're going to talk about concentrations. Um, and so these concentrations important for a lot of different reasons. What it really is you're describing the amount of a particular substance that is dissolved in a given volume of water. So this can be contaminants. It can be nutrients that you're trying to remove throughout your wastewater process. Maybe it's the solids or your dissolved oxygen. A lot of times that's important, dissolved oxygen like streams and such. So really, this is all kinds of things. So what concentration really is, it's a mass, so just a certain amount of something, whatever it may be, and it's how much that is per volume of water. So mass divided by volume. And so usually how this is written is milligrams per liter. So milligrams, that's our volume, and then, or sorry, that's our mass, and then liter is our volume. And so milligrams per liter, that's the same thing as parts per million. So a lot of the times you'll see these being used interchangeably. So just know if you see something in a question or at your own plant that's part per million, know that you can just cross out that parts per million and write milligrams per liter because it's the exact same thing. And then also 10,000 milligrams per liter is also equal to 1%. So a lot of times you'll see percent in chemicals. So a lot of times, like chlorine's a good example. So sodium hypochlorite is usually about 12 to 13%. So that's like 12% of that solution is chlorine, where the other 88% is just water. So um, or that 12% of that is actually the chlorine that's actually going to do stuff. So you have to take that into account when you're adding a chemical to anything, because a lot of the times it's not completely pure. It's only it's in a solution with water already. Okay, so concentration example. So how do we calculate concentrations? So here's just one example. So say you want to prepare a wastewater sample, a simulation to test an experimental wastewater treatment process. So you add 343 milligrams, so there's our mass, of ammonia into 5 liters of water, and there's our volume. So what is the ammonia concentration of this wastewater sample? So this one's pretty straightforward. It gives us our mass and it gives us our volume right there. So we come out with a concentration of equals the 343 milligrams divided by 5 liters. So if we plug that into our calculator and divide those values, we come up with 68.6 milligrams per liter. Okay. So now I'm going to have you all do one, but this one's going to be a little bit different. So instead of giving you these two volumes, the mass and the volume, those two units, this is going to be a little bit different. And this is probably going to be more applicable on what you're doing, maybe if you're in a lab. So you're preparing a calibration standard, and you need to make a 50 milligram per liter solution. So how many milligrams of pure dry chemical do you need to add to a 500 milliliter flask of water in order to make a 50 milligram per liter concentration? Okay, so this is multiple choice. So I'll have you all do this one and I'll put up the poll. And this one's going to be, there's a few extra steps to this one. So if you feel stuck, just give it a minute and I'll start calculating this out. Okay, so I just launched that poll. So you can start calculating this out and let us know what answer you get. And in just a second, I'll start going through this as well. This one is a little tricky. And if you get the wrong answer, don't worry. This one has a few tricks in it. Okay, so take a look at your screen if you're having problems with this one. I'll go over this in just maybe 30 more seconds. Maybe about 10 more seconds. And I'm going to end this poll and share the results. Okay, so nice job. So it looks like there was quite a few different answers for this one, and that's okay. So 25 milligrams was the most popular answer, with 50% of people saying that one. So great. And then some of these other ones have a few people answering as well. So let's go over this together, and hopefully this makes sense. And I'll explain the few hurdles I put in this one. So this is a tricky one. So good job. Okay, so what I did first is I just wrote down my equation. So this concentration equals mass divided by volume. So in our question, though, it gives us 2 out of 3 of these, which is what we need to solve it. But they're not the same as the last example we had. It gives us the concentration because that's what we want to have for our standard that we're making. And it gives us this volume of water. So we're using a volumetric flask and we're making this solution. So we need to figure out how much of this powder we need to add to make this solution. So the first thing we need to do, though, when we have this written down after we put in our values, we need to rearrange the equation. So maybe this is a good time to use those Davidson pi wheels, because I think this is one of the useful benefits of those. But I generally don't use those, so I'm just cross multiply. So this is a basic math concept that is called cross multiplication to figure out what, because our unknown is over here and this is as this mass. So I'm going to cross multiply this way. So 50 milligrams per liter times 500 milligrams per liter equals this unknown. So if you're not familiar with that cross multiplication, let me know, or you can do some Googling, and there's lots of information out there, but I'm happy to help anybody with that to figure that out. And so then we end up with this equation. So this 50 milligrams per liter times 500 milligrams per liter equals the mass. And so we can just calculate this through, but we want to end up with a mass as our unit, which is just milligrams. And so we want to cancel out our liters. And so in this example, this is a good example of when the units you want to cancel out don't match. Because over here we have liter and over here we have milliliter. And so those are the same measurement, but we need to use a conversion factor to get those into the same unit. So I want to put those both into the liter unit as opposed to a milliliter. So if you're familiar with the metric system, there's 1,000 milliliters in a liter, which I should have written down that conversion factor on the slide, but I didn't. But so that means we need to move our decimal place 3 places. So 500 milliliters, if we move our decimal 3 places, 1, 2, 3, it's going to be 0.5 liters. So it's half of a liter. And so now our liters are in the same units. So now we can cancel those out. There we go. So we cancel out those liters. And so now our only unit we have left is milligrams. And so that is a That's a measurement of mass. So now we have our right answer as 25 milligrams. So that's how many milligrams we'd have to add to this solution, this flask, and then add to that amount of water to get our 50 milligram per liter solution. And sometimes you do have to make this if you're in a lab and you're trying to make a standard to maybe calibrate your probe, or do all kinds of different things. So let me know in the chat if you have any questions about that, or feel free to raise your hand and unmute. That one was a little bit of a tricky one, but I just wanted to throw in an example where you had to rearrange those equations and one where you had to make sure you're in the same units, because some things like that will pop up on the exam. Okay, so we're getting towards the end here. We have a few more minutes. I think maybe this is our last concept. So we'll go over this pretty quick. This percent removal. And this is the amount of a contaminant that you're removing throughout your treatment. So it's in a percentage form. So this is really helpful if you have a plant and you're trying to figure out what amount, what's coming in and then what's going out. So you may need to do this for your NPDES permit, for your regulatory requirements. And it gives you some information to know how well your plant is functioning, how well it's doing its job. And if maybe an engineer says that you're going to be able to remove 90% of some contaminant or something like that, you can actually measure this, figure out if it's working correctly, how it's been designed. So this removal efficiency, this equation is down here, and this is straight from that ABC formula sheet. So it's the concentration going in minus the concentration going out, divided by the concentration of what's going in. And then that's going to leave you as a decimal place. So to turn it into a percent, you just have to multiply it by 100. Okay, so we'll do an example really quick, and hopefully that makes a bit more sense. Okay, so the BOD, the biological oxygen demand, of your raw wastewater is 220 milligrams per liter. What is the percent removal of a primary clarifier if the clarifier effluent contains 56 milligram per liter BOD? So this is what we're going to do together. All right, so I'm just going to write down my equation. We'll just use the equation right there, and we're just going to plug in our values. So it's the influent. So it starts out at 220 milligrams per liter. So that's our concentration going into our plant. It's being at 56 milligrams per liter. And then we're going to divide all of that by the influent, which is 220 milligrams per liter. Okay, and so we need to do our order of operations here, of course. And so we want to do, I guess this is the top of our equation, is we can think of that as being in parentheses, that is in the denominator. So we want to subtract those out. And so that leaves us with 164 milligrams per liter divided by 220. So we just divide those in our calculator and then multiply by 100. And our units cancel out. So there aren't really any units left. So it's just a percentage. So our answer is going to be 74.5. So that means that your plant is removing about 75% of the BOD that's coming in as the raw wastewater. Okay, so we have a few minutes left, but let's try to do one of these together, or not on your own, sorry. And I'm going to start this poll. So this is going to be pretty much the same thing. Same concept. So this is with my nitrogen though. So the nitrogen concentration of raw wastewater is 35 milligrams per liter. So that's what's coming into your plant. And what is the percent removal if the effluent contains 13 milligrams per liter nitrogen? Okay, so I'll put up this last poll and we'll give you a few minutes to get this, and then we'll call it a day, and then we can answer any questions. So I'll be around for a few minutes after the top of the hour. So feel free to stick around and ask some questions, but we'll finish with this. This will be our last question. Okay. We'll give you about a minute or so because that's what we got for time. All right, I set that up on the screen already. If you need some guidance setting it up. And a lot of you have already answered, so I'm going to close this poll in about 10 seconds. So put your answer in now if you have it. I'm sorry, this was a bit quick, but I want to end it pretty close to the top of the hour. Okay, so I'm going to end that poll and share the results. Okay, so most people said 63%. So awesome job. Let's go through and we'll do that calculation really quick. Okay, so first what I did is I just put in my values into this equation. So the influent concentration versus minus the effluent concentration divided by the influent concentration. Then we subtracted those first, and then we divided by 35. And so if we divide 22 divided by 35 on our calculator, and then we're going to get 0.63, but then if we multiply it by 100, we're going to get 63%. So that's going to be our answer. So our plant is removing 63% of the nitrogen that's coming in. Okay. So great job, everybody. That's it. So thank you all for being here. Thank you to our interpreters. Very much appreciate you being here. And then here's AJ and my emails.